Welcome everyone. This is Symmetric Functions and Representation Theory, a graduate course at UMass Amherst, and we have some students of the University Sergio Arboleda also taking the course. The overview of the course is I'm first going to talk about group representations, then we're going to talk about representations of the symmetric group, and then we're going to talk about symmetric functions and the relation it has with the representation theory of the symmetric group. And then we're going to talk about a new approach by Okunkov, Vershik, and Olshansky to both the representation theory of the symmetric group and symmetric functions that used some material that was known but not emphasized and some new ideas. And this goes back to 1996 and 2004. Whereas the theory of symmetric functions and the relation to combinatorics was developed mostly on the 20th century, and the representation of the symmetric group dates back to the 19th century, to work with Frobenius. So what are the prerequisites for the course? So mainly having taken a course in discrete mathematics and a familiarity with basic group theory. So what's a group, conjugacy classes, we'll review some of this, and linear algebra. Okay, so let's begin. So the goal today is to give a teaser of what's going to come. So I'm going to give a teaser on representation theory. And our main textbook for the first 3 points I just mentioned is the book by Bruce Sagan, The Symmetric Group, Representations, Combinatorial Algorithms, and Symmetric Functions. Okay, so let's start. So G for me is going to be a finite group. And unless I mention otherwise, it's going to be finite. So this means, I have a set that has an identity and has one binary operation such that it has associativity and you have invertibility. So, okay, and maybe the main example for us is going to be the symmetric group. So this is the symmetric group on n elements. And there's two ways we're going to represent the elements in the symmetric group. So the first way is writing the image of, for example, pi 1 is the image of 1 of the permutation pi 2 is the image of 2, and so on. Okay, so this is one-line notation. Okay, so again, this is kind of standing for 1 gets sent to pi 1, 2 gets sent to pi 2, and so on, n gets sent to pi n. Okay, so that's one-line notation. And there's also cycle notation, where we write the permutation as a product of cycles. So here we have pi I, and then we apply pi again. Okay, and so on until we get back to the beginning. So k is the smallest number such that the image of I is, again, pi of I, and we write it this way. So this should be here. I goes to pi I, then it goes to pi composed with pi of I, and so on. And this is indicating that pi k of I is back to being I. Okay? And this is the cycle notation. Okay? Okay, so for example, if my permutation is 3 4, 5, 2, 1, 6. This means that pi 1 gets into 3, pi 2 gets into 4, pi 3 gets into 5, pi 4 gets into 2, pi 5 gets into 1, and pi 6 is equal to 6, so it stays fixed. So that would be one-line notation, and if I write it as a product of cycles, I would say that 1 gets sent to 3, 3 gets sent to 5, and 5 gets sent to 1. So I close it here, and then 2 gets mapped to 4, and we see 4 gets mapped to 2, and 6 is a fixed point, stays like that. Okay, and then recall that this, we would say that this has cycle type 3, 2, 1, which is the lengths of these cycles we have here. Okay, we will review this, but something called a conjugacy class of the symmetric group, these are indexed by these lists of integers, the length of the cycles, so they're indexed by integer partitions. Okay, so these are sequences of integers that are weakly decreasing. Okay, like this one. Okay, and we'll review what this, how many permutations have a given cycle type. Okay, what else do we maybe remember from permutations? Maybe you've seen the sign of a permutation. So remember, a permutation is either even or odd, and you might have studied the subgroup of even permutations when you saw group theory. So to each permutation, we can assign a sign, and this is minus 1 to the k, where k is, so let me define k. Sorry, just give me a second. So again, the sign of pi is minus 1 to the k, where k is where pi, so if pi can be written as a product of k transpositions, where where ti is what I call what we call an adjacent transposition. Okay, so our example from before, this permutation had 1 going to 3, going to 5, going back to 1, 2 going to 4, and 3. And if I want to know the sign of this, well, it happens that the sign of two permutations, the product of two permutations, and by the way, I'm multiplying permutations from right to left. It so happens that this is multiplicative. So if I want to know the sign of this permutation here, well, it's enough to know the sign of each of the cycles. And from this definition or other considerations, well, 3 doesn't do anything, doesn't change the sign. It's a fixed point. Oh, this should be 6. Sorry, it's a fixed point. We have the transposition 2 and 4, so that just this transposition has sign minus 1, and this 3 cycle has sign, well, it has even sign, it has sign 1. Okay, so in total I have sign 1, sign minus 1, sign 1. So global pi has sign minus 1. So the sign of pi is minus 1. Okay, and you can try to write this by an odd number of adjacent transpositions. Okay, so maybe let me here ask an aside. So the symmetric group is generated by this adjacent transpositions. So you can generate the symmetric group with n-1 generators. So what's the minimum number of generators you need? What's the minimum number generators of the symmetric group. Okay, so maybe think about that, and it might tell you the answer next time. Okay, all right. So that's kind of some refresher of some work of some stuff of the symmetric group. So now let's make a definition of our representation. So maybe before I jump into this, what's the goal of representation theory? Well, loosely speaking, we want to study the symmetry of groups with linear spaces. Oh. So, i.e., with subspaces. So we want to use linear algebra, matrices, and so on to study the symmetries of groups. Okay, because groups can be complicated. So maybe the symmetric group, you might think it's not so complicated, but for instance, it's a group with a large size. It has n factorial elements, and maybe you've heard of a group called the monster group. So we want to study groups that can be inherently complicated, non-commutative, and so on, with linear spaces, matrices, which are simpler still, non-commutative, but simpler. Okay, so let's kind of dig into one of these, into definition of our representation. So a matrix representation of G of degree D is a group homomorphism. So that's kind of a big word, but we'll digest it in a second. From the group to GLD. So what's GLD? This is the set of D by D invertible matrices with entries in C. Okay. Okay. So what is group homomorphism mean? What does this mean? So an equivalent statement is I want a map that sends to each element in the group and associates an invertible matrix, and has to satisfy the following properties. The identity element of the group, denoted here by epsilon, has to be sent to the D by D identity matrix. And if I look at what is the associated matrix to the product of two elements G and H, it should be the product of the respective matrices XG and XH. Okay? Oh, too much. Okay, so let me keep this here. Okay, let me move this down out of the way. And so here's the definition from before. Okay, so now let's look at some examples. Well, if so what's an example of a degree 1 representation? So if we send xg to be just 1, the complex number 1, for all g, this is a representation. You can check and this one's called the trivial representation. That's my first example. Second example could be, maybe if I have the symmetric group, I'm going to send a permutation. So again, this is degree 1. I'm going to send the permutation to the sign. Okay, so I'm associating to each permutation either 1 or -1, and because of the thing we just said, that the sign of the product of two permutations is the product of the signs, this is a representation. So it satisfies this condition here. Okay, so this is an example of a degree 1 representation. Okay, and we would say it's non-trivial because it's not sending everything to 1. So when you saw the sign of a permutation, you're already seeing an example of a matrix representation. So we study permutations by associating to them 1 or -1. So we study groups, we study symmetries through linear spaces. In this particular example, just a 1 by 1 number, either 1 or -1. Just a 1 by 1 matrix, a number, either 1 or -1. Okay. So now that's for degree 1. What about something of higher degree? So let's stay with a symmetric group, as we will do mostly in this course, and I want something of degree n. So what's a way to associate to a permutation of size n, a permutation of n elements, to associate to it an n by n matrix? So I'll leave you a second to think about that. So the thing that might come to mind is something called a permutation matrix. So I could associate to each matrix, to each permutation pi, I associate to it a d by d, an n by n permutation, matrix. Sorry about that, matrix. And this matrix is a permutation matrix, so it has, so xij is 1 if pi j equals I and 0 otherwise. Okay, so let's do an example. So for n equals 3, say for n equals 3, if I look at what's the corresponding matrix I would associate to the permutation 3, 1, 2. So this is in one-line notation. So this is the permutation that sends 1 to 3, 3 to 2, and 2 to 1. So it's a 3 cycle. Okay. So how do I find this matrix? Well, so I send 1 to 3. So in the first column, I have a 1 on the third row. I send 2 to 1. So in my second column, I have a 1 on the first row. And then I send 3 to 2. So in my third column, I have a 1 on the second row. Okay, so this is what the convention here is saying. Okay, so, and the rest are zeros. Okay, so that's the permutation matrix of the permutation 3, 1, 2. And this is a representation because, again, you send the identity to the identity matrix, and maybe you remember that the permutation matrix of a product of permutations is the product of the permutation matrices. So it's a representation, and it's of degree t. And this one has a name. So yeah, the one, I guess, the example 2 was the sign representation. Okay, and this one about the permutation matrix is called the defining representation of the symmetric group. Okay, so look at that. When you saw group theory, when you studied permutations, you kind of studied 3 matrix representations of the symmetric group already. The trivial one, assigning to every permutation 1. The sign representation, where you assign 1 or -1 if the permutation is even or odd. And just associating to each permutation, representing each permutation by a permutation matrix. Okay? Good. So that's an example of a matrix representation. Okay, so what do we do with these representations? What kind of questions do we ask? So, well, sometimes our representation can be broken into smaller representations. And analogously, sometimes we can put together representations to form bigger representations. So let me give some intuition for this. So this is what I would call reducibility. So so we say that if we have a representation x, of G is reducible, okay, if there is a basis, so a basis of CD, so this is so I guess I'm assuming that this is a degree D representation. So if I have degree D representation, it's reducible if there's a basis of CD B such that xg, so that for all elements in my group, the matrix xg looks like this. It has the following block form. Okay. So if I can find a basis B so that xg has this form where all these blocks have the same size, all these block matrices have the same sizes for all G. So by size I mean that this A is, well, it has to be also square, so this is K by K, and this is N minus K by K, and this is, so this one is also square. So this is N minus K times N minus K, and so on, okay? So A and C would be square, but the important thing is that the size of the blocks, this K and this N minus K, stay the same throughout throughout all the elements of the group. Okay, and this lower block is a zero matrix. Okay, so we'll discuss what this means later in the lectures, but let's have this working definition. So if I can find the basis of CD such that I can break, I can write each of the matrices associated to G in this block form where I have this like zero block here, then I am reducible. Okay? So let's look at some examples. So our first example was the trivial representation. Well, that's of degree 1, so I cannot really break into blocks a 1 by 1 matrix, a number. So this is not reducible, so we would say it's irreducible. Okay? That's the trivial one. That was our first degree 1 example. So the trivial representation is irreducible, but kind of for silly reasons. The sign representation is also reducible because it's of degree 1. You cannot break a 1 by 1 number. Okay? Okay, then what's maybe the other one we've seen? We've seen the sign representation. So how about that one? Oh, nope, that's old. Yeah. So what can we say about the defining representation? Is it irreducible? So let's just go small. So let's try n equals 2. Okay, so what's happening here? Well, so I'm writing this in one line notation. To the identity, I associate the identity permutation matrix, and to the other permutation to 1, I associate the matrix, this matrix here. Okay. where this is a 0. Okay. So well, so I don't seem to have this block form because this is kind of the only thing I can do because I just have 2 by 2 matrices. But this is a 0 here below, but this is not a 0 here. So the standard basis is not doing the trick. But there might be another basis that does this. So can you think of one? So maybe a hint of this to see how we could build such a thing is to notice that if you have a permutation matrix and you act on like E1, so this is the vector E1, well, it sends it to E2. So a permutation matrix sends EI to EJ if the permutation sends pi I to J. Makes sense, right? So a permutation matrix is moving these elementary vectors according to what the permutation is doing, like the way the permutation is acting on the elements 1 up to n. So definitely you're not you're going to be moving all these elementary vectors, or maybe you're fixing some, but we might need to look for other types of bases, not just the elementary vectors. But because of this, you can combine vectors, you can add them. So if you take, let W, and we just add the vectors E1 and E2, okay, then, well, the identity is not doing much to this. So by linearity, this is what happens when you multiply the matrix by E1, so it's just going to be E1, and when you apply it to E2, you just get E2. So that's fixed. But the other permutation matrix is also fixing this vector because you're getting, well, it sends E1 to E2 and it sends E2 to E1. But this is just the same vector you had before. So if we take a basis that has this sum of two vectors first and anything that makes it independent after, you can check that now the permutation, when you change the basis, the matrix of this so the matrix corresponding to the identity is still going to be the identity, but now when you look at the one of 2, 1 with respect to P, that's going to be, well, I know that I'm fixing E1, E2, but now I send E2 to E1. So since E1, which is what happens if you multiply E2, like the matrix to E2, so E1, if I write it with respect to this basis, it's going to be E1 plus E2 minus E2. So in terms of the matrix with respect to this basis, this is going to be 1 minus 1. And voila! Now we do have this block form across all the elements, all the two permutations. You see, I have the 0 below in the same position. So because of this, the defining representation is not irreducible. It is reducible. So the defining representation is reducible. Okay. Okay. So, so we kind of had to do some work, and this is just a degree 2 representation. So how can we tell in general if a representation of, say, the symmetric group is irreducible? So that's a question we're going to worry about. When is a representation of the symmetric group or of a group irreducible? Okay, so this is a question we're gonna care about. So yes, so there's something a bit better than reducibility, and it's being decomposable. So we say that a representation, so X, a matrix representation, is decomposable as into two pieces. Well, these pieces are special. They're called subrepresentations. If there is a basis that makes it block diagonal. So a bit better. So now we want AG. We want to have 0 here, and CG. So now I want to have kind of this block diagonal form. Okay, so I want this 0 block here, and I want this 0 block here. Okay, and and when this happens, I say that X, the representation X, is a direct sum of the representations A and C. Because I'm kind of acting by blocks. So this block, if I have the same size for all permutations G, then this block by itself is a smaller degree matrix representation, and the same for C. Okay. So let's go back to our defining example. So where we left it was with this basis. Okay, and it gave us sorry, I should write B prime here. So it gave us the identity, and for the other permutation we got 1 minus 1. Oh, and this was, I believe, a 1. Okay, so it's not quite there because of this 1 here we have. Sorry, the one right here. Okay, but let's see if we can do better. So if we let B prime be E1 plus E2, and this is E2 minus E1, so something that kind of makes it kind of orthogonal, then we can check that X12 is still, of course, the identity, because I'm just the identity matrix to be in the elementary basis. But now the permutation to 1. Now, I'm still going to send E1 plus E2 to itself, but then E2 minus E1, well, E2 is going to be sent to E1, and E1 is going to be sent to E2, so I'm going to get minus this vector, but that's kind of on the same line. So this is going to be 0 minus 1. So now you see I'm even better than having this lower block on the lower left being 0, but I have also a 0 block on the top right. So I'm block diagonal with the same sizes. Okay? And if you look at the 1, 1 block, it's just always 1 for each of the permutations. So that looks like a degree 1 representation, the identity the trivial representation. And this lower block is 1 at the identity and minus 1 at 2, 1. So does that remind us of a degree 1 representation? Yes, the sign representation. So this is indicating that the defining representation decomposes into the trivial representation and the sign representation. So that's pretty neat. Okay, because this lower block, it's either 1 or minus 1, so it's behaving like the sign representation. Okay, and as n grows, we're going to have more pieces, but we're going to see how you decompose. So it won't be just two pieces. Okay, so that's kind of a very brief overview of representations and representations of symmetric group. But now I want to mention a little bit about symmetric functions. So we're going to consider functions, say with complex coefficients, but they're going to be power series in a countable number of indeterminates, so x1, x2, and so on. So you might have looked at power series in combinatorics, and you sometimes have only one variable, like for example 1 plus x squared, ... But now we're going to consider power series with many indeterminates. Okay, so when you have such a function, well, there's a natural action of the symmetric group. Namely, if you have your well, so I guess this is the definition. Okay. So if you have your multivariate power series, we let the permutation act by just permuting the variables. Okay, and I guess here the permutation has only size n, so any indeterminate beyond that just stays the same. Okay, so that's how it acts. Okay, and we say that f is symmetric if it remains the same after this action. If it stays the same for all permutations. Okay, so if you permute the variables in any possible way, you stay the same. Okay, that's what it means for a multivariate function to be symmetric. Okay, so let's look at some examples. Well, if I just add x1 plus x2 plus x3 ... then this is symmetric, because if no matter how I permute the variables, I just stay the same. Okay. Okay. But for example, something like x1, x2 just by itself is not symmetric. So does that make? Oh, sorry. I guess I forgot one little thing. Sorry about this. This is true for all n. So not just so for all permutations and for all n. Okay, because I have a countable number of variables. I have x1, x2. I don't I don't have just n variables. So in order for it to be symmetric, it has to be true for all permutations of all sizes. Okay. So that's why x1, x2 is not symmetric, because, for instance, if the coefficient of x1, x2 is 1, well, for example, I have no x1, x3, so that means the coefficient is 0. But therefore x3. Okay, so this coefficient is 0. So therefore, if I have a permutation that sends 2 to 3, okay, so if this is my permutation and it acts on x1, x2, I'm going to get x1, x3, which is not the same. Okay. Okay, so is that clear? Okay. Okay, so that's an example of a symmetric function, and so symmetric functions form a ring. So they have, if you add or multiply symmetric functions, it stays symmetric. If you scale them as well. So we're going to study this ring of symmetric functions. So it's denoted by capital lambda. So this is the ring of symmetric functions in belongs to this set of power series we had before. Okay, and this ring, so as a vector space over C, has several bases. So it has several interesting bases. So let me show you a picture of, well, kind of some of these bases. So, whoa. So this ring has different bases, and here's a picture from a very famous textbook by MacDonald. So there's many more, but here are some of the bases. So the easiest one to understand is monomial, but we'll explain it later. There's also one called power sum that was, so for example, studied by Newton in a famous result of symmetric functions. There's also the elementary symmetric functions. There's another one called complete, and there's one called even forgotten, and which I kind of forgot the definition of it. And then here at the top of this hexagon is the Schur. It's this function called S lambda, which is called the Schur function. So it's named after Isaiah Schur. And you might notice that all these bases are indexed by these lambdas, and we saw lambdas before today indexing partitions, integer partitions. So in fact, integer partitions are indexing these bases. So if you say restrict by the degree of the symmetric functions, you get a subspace. And the dimension of this subspace of, say, degree d symmetric functions is the number of partitions of the integer d. So if you liked integer partitions, now we're going to study vector spaces whose dimension is the number of integer partitions. So that's kind of pretty cool. But anyway, so the Schur here is on top, and there's a reason for that. Because, well, imagine we saw that x1 plus x2 and so on is symmetric. So imagine I take two copies of this, so x1, x2, x2, the sum squared. How do I write it in different bases? So for example, how do I write it on these Schur functions? So that's kind of hard because I haven't explained to you what a Schur function is. But if we postpone this later, and you might believe me that the Schur function of the partition 1, 1 is this written here. Maybe it's quite small. X1 plus x2 plus x1 plus x3 plus dot dot dot. And you might also believe me that the Schur function s of the partition 2 is just x1 squared plus x2 squared plus dot dot dot. So meaning that's since you're symmetric, you need to have all these other monomials like x3 squared and so on. But you also have plus x1 x2 plus x1 x3 plus x1 x4 plus x2 x3 dot dot dot. Okay, so maybe if you believe me for now that these two are the same, then if I want to answer how to write this x1 plus x2 dot dot squared, if I want to write it in terms of these two functions s11, s22, well, just expanding, just using, just squaring and not doing what we call the freshman dream, well, this is the sum of the xi squares plus twice the mixed sums, right? Well, so if you write this in terms of these bases, you're going to need one copy of S2 plus one copy of S1. So I want you to remember this. So it's just going to be summing these two functions with the coefficient 1. Okay? So the thing is that there's a very deep connection between the representation theory of the symmetric group and symmetric functions. To each representation of the symmetric group, we can actually associate a symmetric function. So we will see this. So the details are I want just to get the idea across. But let's see what would happen for the defining representation of the symmetric group of size 2. So if we do this, the associated symmetric function is going to be exactly this one we've seen, x1 plus x2 dot 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 squared. So I'm right here. Okay? So we will see that the expansion of such a symmetric function in the Schur basis, this S lambda that was on top of this hexagon before, encodes the decomposition of the original representation into these pieces that are called irreducible. So maybe you remember that we saw that the defining representation was the direct sum of the trivial representation and the sign representation? Well, there's only one copy of the trivial one and only one copy of the sign. And these two ones, so let me just maybe put some colors here. So this one corresponds to this one here. And this one here corresponds to this one. So to answer the problem of how to decompose a representation of the symmetric group into these irreducible pieces, I could study its associated symmetric function and just solve the linear algebra problem, and but just is kind of on quotation marks, solve the linear algebra problem of expanding it into a basis. So just doing linear algebra. Okay? So this is just a little teaser of the first 3 parts of the book, of the course. And we'll start with definitions and more details and go more slowly on the next lecture.